Hi everybody, this video is going to be about molar conversions. We're going to be using dimensional analysis to do the same types of conversions we've done before, but this time instead of using things like inches and feet or minutes and seconds, we're going to use some units that are a little more applicable to chemistry. We're going to be using things like molar mass, the mole, grams, stuff like that. If you're using the note-taking sheet that you can print from the website, you can set your notebook up like this. You'll take your notes on the template that you can print, add your KCQ boxes at the end for homework as usual. So molar conversions are conversions that are related to moles, exactly like what it sounds like. We are still using dimensional analysis. One of the things that's actually nice about molar conversions is your pathway is very limited. On the earlier types of dimensional analysis problems we've been doing, you had so many options to choose from, so many different conversion factors and pathways you could take. But for molar conversions, this is your only set of pathways that you can use. You can go from grams to moles, you can go moles to molecules, you can go backwards, you could go molecules to moles or moles to grams, but you cannot do something like go from grams directly to molecules. We do not have a conversion factor for that. We're going to be using little baby steps like our frog hopping on lily pads to get to the other side of the pond. So to go from grams to moles or vice versa, you'll use molar mass. Remember, molar mass is different depending on which molecule you're using. So it'll have some number of grams over 1 mole. By definition, molar mass is how much 1 mole of something weighs. So the X here can change based on the formula, but the 1 mole has to stay the same. It's always going to be 1 mole. That's like saying 1 dozen is 12 donuts. By definition, that's how many are in 1 dozen. To go back and forth between moles and molecules, you'll use Avogadro's number. 6.02 times 10 to the 23rd molecules per 1 mole. It has to be a 1, you can't change that. If you want to be a little more generic, instead of saying molecules, remember you can say particles. So if you want to be more generic, maybe instead of molecules you have atoms, for example, you would just say particles or swap it for the more specific unit. But usually we're doing molecules in a chemistry class. So for this example, we're trying to figure out how many grams does 1.7 moles of sodium chloride weigh. So my pathway is picked for me. I don't get to do anything different. These are my only options. And I'm going to go from grams to moles. So I don't even need the molecule part. It's just one simple single step. We will need molar mass. So I need to look at my actual formula for sodium chloride and figure out that the molar mass is 22.99 for sodium. And I'm adding in the mass of my chlorine, which is 35.45. When I add those together, I get 58.44 grams per mole. Remember that I'm getting these numbers from the periodic table. That's where those numbers are coming from. So now this is my conversion factor. My molar mass becomes my conversion factor. So I start with my known value. I'm going to use my line method. I'm going to see that I'm trying to cancel moles. So 1 mole goes on the bottom. By definition, molar mass is how much 1 mole of something weighs. And because it's sodium chloride, I'm going to have 58.44 grams on the top. My moles cancel. I'm left with grams. I punch that in my calculator and I get 99.35 for my grams. This time, let's try going backwards. Let's start with grams and go to moles. So I have my molar pathway, but I'm only going to use this portion. This time I'm going from moles to grams. I still use molar mass. This time it's the molar mass of carbon dioxide. So here I use my periodic table. Here's my mass of carbon. And here's my mass of oxygen. And I have 2 oxygens here. So I add that up. 44.01 grams per mole becomes my conversion factor. I start with my known value. I want to cancel grams, so this time the 44 is going to go on the bottom and 1 mole goes on top. By definition, molar mass is how much 1 mole weighs, so I have to make sure it's a 1 there. Grams cancels, I'm left with moles, punch it in my calculator, and I find out if I had 14 grams of carbon dioxide, I really have 0.32 moles of carbon dioxide. Let's try moles to molecules. Here's my molar pathway, but this time I'm only going to use that part. When I go moles to molecules, I'll use Avogadro's number. The nice thing about his number is it's always the same. With molar mass, I have to change it each time depending on the formula, but Avogadro's number will always be the same. I start with my known value. Because I want to get rid of moles, I'm going to put 1 mole on the bottom. And I'm going to have Avogadro's number on the top. Because it's water, I am going to say molecules. You could say particles if you want to be more generic. That's always fine. I punch that in my calculator. And I'm going to get that 5.3 moles of water has 3.19 times 10 to the 24 molecules in it. Let's go the opposite direction. This time molecules to moles. I'm still going to use Avogadro's number. It's not going to change. I start with my known value. It's okay that it's scientific notation. It doesn't matter. If I want molecules to cancel, I'm going to need to put Avogadro's number on the bottom, and 1 mole will be on the top. Molecules will cancel. I'll be left with moles. If you do this correctly and you use the parentheses correctly, this is the number you will get. You have to make sure that you put parentheses on the bottom of that fraction to keep your scientific notation on the bottom. If you're not careful in your calculator, it's going to get confused and it's going to think this times 10 to the 23rd should be on the top, which is not correct. We don't want that. We want to make sure that our parentheses keep it on the bottom. If you ever get a number that seems way too big compared to what you should have gotten, then that's telling you that you probably forgot your parentheses. That is probably the #1 mistake we see all school year. All right, now let's go from grams to molecules. Here's our molar pathway, but this time we are going to have to use the entire thing. We're going to use molar mass first, then we're going to use Avogadro's number. This molar mass here is the molar mass of water, H2O. I got that from the periodic table. 2 hydrogens plus an oxygen. Start with my known value. I want to get rid of grams. So my 18 is going to go on the bottom. For the sake of space on this PowerPoint, I'm just going to put 18. I'm not going to put 18.02. It's not a big deal. Remember, we don't care too much about the decimals in this class. The 1 mole goes on the top. The units cancel. So now I'm going to get rid of the moles by putting 1 mole on the bottom. Avogadro's number goes on top. Moles cancels. I'm left with molecules. Punch it in my calculator, and that's the answer that I get. Going from molecules to grams, once again I'm going to have to use the entire molar pathway, but this time I'm going backwards. Molecules to moles, moles to grams. I'll use Avogadro's number first, then I'll use molar mass. This time it's the molar mass of CH4. If I look on the periodic table, carbon weighs 12. I have 4 hydrogens that each weigh 1, so I get a mass of 16. I start with my known value. Avogadro's number comes next. To get rid of molecules, it's going to go on the bottom. 1 mole is going to go on the top. Molecules cancels. I'm going to then use molar mass, which is 1 mole on the bottom, 16 on the top. That way moles cancels. I'll be left with grams. Because we have that scientific notation on the bottom, we have to be really careful that we're using our parentheses in our calculator. We want to make sure that we keep that 10 to the 23rd down on the denominator. We don't want our calculator confused and flipping it up to the top. So if I have 2.6 times 10 to the 25 molecules of CH4, it would weigh about 693 grams. And just a little reminder that you can be generic, you can use particles instead. So Avogadro's number, instead of using molecules, it could have been particles, it could be atoms, it could be soda cans, it could be cars. It doesn't really matter what you're counting. It's just talking about whatever item it is that you're counting. Alright, that's it for this video. I hope it was helpful. Bye everybody. Now